next talk. So now it will be Zhang, who, so Zhang is a senior researcher at the All Data AI group at Microsoft Research in Cambridge. So she's currently leading the project Azure on data efficient decision making. And she's interested in both machine learning theory, Bayesian deep learning, approximate inference, causality, Bayesian experimental design, and reinforcement learning for sequential decision making, as well as various machine learning applications with business and social impact. So she will talk today about simultaneous missing value imputation and causal discovery. And without further ado, Cheng, I give you the floor.
Thank you very much. Can someone help me to let me know how can I share the screen?
Sorry, share the screen.
Let me make you a panelist. It may not have happened.
Yeah.
Sorry.
So again, we have like 35 minutes in total and then 10 minutes for questions.
Can everyone see my screen now?
Yes.
Yeah.
Fantastic. Thank you very much for the introduction and invitation to this fantastic workshop. So today I'm going to talk about efficient decision-making with causal Bayesian deep learning. So I put parentheses on causal. So for the first part of the talk, I'll talk a little bit about the non-causal way, how we did decision-making with Bayesian deep learning. And in the later part, I'll talk a little bit about how causality helped and how did we use it to do simultaneously causal discovery and decision-making at the same time. So let's start. So, as the introduction said, I lead the project, and our aim is to do automated efficient decision-making. And we actually really want to get inspired from human decision-making because we are really efficient. And so if I think about how the human expert want to make decisions, what's the properties made these decisions efficient? So I summarized 3 points. So first, human expert can make decisions under any situation. It can be partial observation, and it also comes with uncertainty estimation. And secondly, the human decision-making commonly is very efficient due to we do personalization. So we act differently in different situations. And lastly, our decision-making is robust in different environments. And let's look at some examples just to show it. So if a medical doctor, a human expert, to see a patient with broken arm and potentially will give an X-ray scan. So does a teacher see a 7-year-old, probably will ask, what's 3 multiplied by 7? And I think she will never ask about what's Monte Carlo integration. The same for example, marketing experts and all this. So what do you see here is they just see part of the data. In some way, they never know everything because they need to make a decision. So they can make certain judgment. And secondly, they adapt how they interact with the user due to their estimation in a very personalized way. And you all know, like I think the teacher will not change the behavior if a 7-year-old is having a jeans on or having a skirt on. So the current machine learning, I think everyone agrees in the past years, deep learning have a lot of success stories. However, it doesn't satisfy all these 3 criteria I just mentioned. It doesn't uncertain estimation, it's debatable. It doesn't handle partial observation efficiently. It doesn't make decision in a personalized way. And we all know it is vulnerable sometimes. And so it does not provide the robust in the way that we desire in the decision-making. So the goal for the whole project and for the whole talk is how can we make decision as efficient as human using machine learning. So we want to do decision-making on any data. We want to do personalized decision-making to be efficient, and we want the whole process, the whole system to be robust and interpretable. And with this, let's recall one of the example again. So for Alice is coughing, and Bob asked Alice to take the temperature. And then Alice had really bad fever. They decided to go to the hospital. So what happens in Bob's mind is, seeing Alice coughing, Bob can estimate everything, have uncertain estimation for everything possible. Alice may have cold. He's very uncertain whether Alice had a fever or not, etc. And based on the task, how to best take care of Alice, and Bob decide to ask Alice to take the temperature. So what happens as a human? So first, it is like making a missing value prediction, right? Because we're estimating the situation, everything unknown with uncertainty, and then we decide what to do next. So this corresponding to the first two goals, like decision-making under any data and personalized decision-making to be efficient. So let's look at the first thing. How can we make a decision under any data? So we translated it to a deep generative model. In particular, we choose a VAE-based framework. I think everyone here knows variational autoencoder. It is a beautiful framework. It kind of combines deep learning and probabilistic inference together. So the model is like a decoder, and the inference network is like an encoder. So it is very efficient. It allows us to have uncertain estimation, but all the success stories is based on fully observed data. How can we make it partially observed? Because in our situation, like a 7-year-old child, potentially the age is the only observation. We don't know the children's skill. We don't know how to put the children in the correct class, right? So this is a partial observation situation. And our goal here first is how to make it working when we only have partially observed data. So the goal is like this: instead of having observed a whole deck and then decode to the whole deck, what we want here is given a partial information, like it's like a half deck, but in this situation, it can be the coughing from Alice, and potentially Bob also knows the age of Alice. And then Bob wants to estimate everything, I don't know, like whether Alice have cold, whether Alice have fever, and all these things. So we want to make a variational autoencoder to something we call partial variational autoencoder, which does, given partial observation, estimate everything that is unknown with uncertainty estimation. So with browsing modeling, and everyone familiar with this type of framework, so we can see that if just with partial observation, we write down our model, we still want to maximize our model evidence, we can construct the elbow exactly in the same way. And for the model, this type of model tells you is given the latent variable, all the observations are independent. So the elbow still hold, the decoder is really easy. And now the challenge is how to design an inference net. So we actually get inspired from computer vision literature and also from set encodings, deep set modeling. So we swap the regular neural network, and we can make the encoder to use this deep set type of framework. So in this way, we can always observe like any subset of information, then we can predict everything that is unknown, and also with probabilistic like estimation, so we know the uncertainty. And so in translate in some way, so if we give a table that can have a lot of column and a lot of row, and then given any subset of observation, we predict every missing entry with probabilistic estimation. So these entries, they can have some targets, and some are just as observation. For example, the body temperature. This is something we potentially want to guess. A patient maybe have fever, or completely healthy person, potentially not, right? So now we achieved our first goal, right? So we can make decision under any partially observed data. And then how can we make personalized decisions? Let's think about like information acquisition. So this will translate the question, like what is the best question to ask? It's like if we're talking about rank vendor system point of view, I guess people use some platform, they ask you a couple of questions, and then they want to use minimum question in a personalized way to identify kind of your personality, your preferences, so that they can give you highest quality recommendation. So this whole procedure is given the limited budget, because every iteration, we don't want to ask that many questions. How can we do it in a personalized way and to be really efficient? The same scenario translates to education, how to put students in the correct class and correct level, translates to like a medical test, as I talked before. So how can we do it? So that also shows why did I really care about uncertain estimation in the first place as well. So in this way, it is thinking about it in this way is, given any partial observation, how can we actively select the next variable? So like we want to select the variable, or in some way select a question to ask that help us most. So in different situations, it's like, how can it help us most, for example, to diagnose the patient? How can it help most to understand the user best, so we can give the best recommendation? So we want to quantify in some way like information gain by asking something, like by actually observing the answer just for one question. How can we do our task better? So then we quantify this information reward using such formulation. So assuming X5 is your target, it describes like a student level. X5 can also be like everything else. So it is a target. And XO is what you already observed. For example, coughing for the Alice case. And XI is like anything, the whole list of questions you can ask. So in this way, we want to find out if you ask XI, so what's the KL divergence on doing the task, on predicting X5? So because you want to ask XI, that makes the biggest difference, because if you ask XI by additionally observing XI, there's no difference, means by asking this question, you really did not get any progress on making doing your task better. So with this formulation, we can quantify in some way how useful to observe something. And so I think if everyone is very familiar with approximate inference, then commonly when you see a KL term like this, you know this is intractable. There are many ways to do it, how to make it computed. We can construct a different bound. We can think about, because this is like an inverse elbow, the KL will need to be as high as possible. So we can construct different bound, and we can also use Bayes rule and to convert it to latent space to make it easier to compute. So we actually came up with efficient approximation so that we can compute this information reward, so that we can enable such interactive system. And so with such interactive system, what we can achieve? These are just some simple machine learning benchmark data sets. Like you can see for each plot, the axis is the steps, it's like how many questions you have asked, and the y-axis is like the error. How good are you making your decision? You can see given any budget, we obtain the best predictive performance, and given a performance requirement, we can achieve it with the lowest cost. So that in this way, think about in real world scenario, so you can actually build an interactive system if you want to be efficient to make your decision like with lowest cost, with lowest number of steps. So these are real, just some machine learning benchmarks, but I'm very proudly say that such system is actually deployed in like one of the British-based company is called ED. As an example before, when there is a new student, you want to place a student at the correct level. You want to know about the student study progress, what is the level, and then you can make a personalized learning path for this student. But the first thing is you want to know the student level. And of course, you don't want to ask a student like 1,000 questions. Of course, in that way, you know the student really well, but the student will, it's a waste of time student, because you never get the student spend days to do such tasks. So we are only having the budget of asking student 10 quizzes, and these quizzes are these multiple choice quizzes. And by the end of the quiz, we want to place the student at the correct learning level so that they can go through a learning path. So the algorithm behind is the system I just told you about, and the product is called Level Booster. So as I mentioned, this can be applied to form a real-world interactive system in many situations. Like it can be in healthcare, it can be real-world survey, it can be, for example, help desk, it can be like for interviewing or recruiting. And furthermore, I want to say that since we had the system, we did many improvements based on the work I just presented, because in real world, there are a lot of real challenges. For example, like the data, if we look at it, the answer may not be multiple choice questions, because then they are all categorical data. It can be mixed. It can be people answer like the age is ordinal, like gender is categorical, and things like blood pressure that is continuous. And for example, some questions even have natural language answers, and that's more complicated. So how can we use such interactive system in real world way? We need to handle mixed type of data. So we did extend our work to handle this heterogeneous mixed type of data, so that we can handle any type of answer and any type of question. And of course, to train such model, we always require the training data. But the fact is, in the real world training data, it is commonly generated from human, because to collect the data, there is human in the loop. We want to help the human for the future, but the historical data are collected by human, and the data missing entry may not be at random, because there is a human bias inside, and it can also be determined by the situation. So it cannot be missing at random. So we also extend the system to really be able to handle like a missing out at random training data to build the system. So I will not go in depth about it, but just want to let you know that for this whole line of research, we have pushed it to be able to handle any real life situation, and it is ready to be used in production. So as I talked, so we enable decision-making under any data, and we also enable personalized decision-making to be efficient. But what about robustness and interpretability, right? So it is known that deep learning are not very robust, and there are paper already shows generative model is a little bit more robust than discriminative model. Although we are in generative model, but I don't think the robustness level is as robust as human decision makers. Although attacks still holds in generative model. But then really reflect on this. Why humans are really robust? So we see a picture of knife, shift a little bit, it's still knife. We see a picture of cat. If the cat just like move outside, it's still a cat. So humans are very robust. And why is that? It is because the modularity property, we know these things are modular, and this corresponds to causal reasoning. So think about just a simple image. So we kind of know what we see is like a picture, like the perception. And this perception can have different modular property, and this can be generated at multiple causes, like it's the image of 7 looks like that is because first it's a digit 7, and it's generated from things with different writing style, and it can potentially have different like a noise injection, shifts, rotation. So humans are good at causal reasoning, and so we can be really robust to prediction. So in this way, we did for the really simple image case, I think we can think this is a causal model, like it is come from the cause is a true label. There's some intrinsic factors that are not easy to manipulate, for example, writing style, or there are some other factors that is, we call it manipulatable. So that is shifts, rotation, adding noise. So all these different attacks are in some way can be summarized by intervention in this manipulatable variable M. In this way, for the really easy image case, what we can do is let's build a model that is consistent with the causal reasoning diagram. So we call it deep causal manipulation augmented model. But what we did is really simple, is given the causal graph, we do the generative model just identical in a way designed for the causal graph. And then if for the generative model, if you remove the two sides, it's a variation autoencoder. We can do the same thing. The generator is, you kind of just factorize the model in the causal way, but the generator is still a deep generative model. And then you can use a similar technique to do the inference. And in this way, you can also encode different type of data. I mean, if your data, maybe clean data in some way, you know what's the M, you can set it to something, like if you know the manipulation. But of course, there are also situations you don't know the manipulation, and you can treat M as just a latent variable, and you can take training data in this mixed way, just to construct an elbow in this separate situation, depends on whether you know the manipulation or not. So it's really flexible, just to making a model, make it causal aware. Let's just see for the classic MNIST situation. This is how it's robust to very popular type vertex. So the blue one, a basic deep neural network, discriminative model, and the different other lines. So it is because we have with the generative model, we can also fine tune it. So the orange line kind of just tells you if we just use a model, you can see it's already much more robust. And the green line tells you if we use a model and in the test time, we can use the test data without label, but just to fine tune the model with the test data per image, we can get to the green line. So you can see it is even more robust. And one more thing is, I plotted the red line, which is on the clean image. What I want to show here, it doesn't matter we fine tune the model or not, because it is causal aware, like the performance on clean data never drops. With causal reasoning, what the side effect, it will naturally give you interpretability. It retrieves a natural disentangled representation in this case. For example, what we tested here is if we give this shifted image to the model, we can generate in some way like a counterfactual images by just use a do operation to set M equals clean. Then you can see the image can be shifted to the center. So the image is really a simple question. Can we use it for general data? Can we use it for tabular data? Can we use it for manual variables? The answer is yes, because if we know the causal graph, we can, if we care a particular target, we just can take the Markov blanket of it, and we can build a deep generative model that exactly is consistent with the causal relationship. And so this can be also like much more robust, and you can think it as this whole model can be combined with what I talked before and used in this interactive system setting. But I'm not sure. So in the paper, we did present some results in synthetic data that is much more robust. However, I'm not showing the results for like as I showed before with real life interactive system. And why is that? Is how can we get the causal relationship? Because think about the real world data. Like for image, we may, in some way, we are the domain knowledge. We kind of domain expert. We kind of can just draw the causal graph that we believe in, and that potentially is very close to the true causal graph and have a lot of nice properties. But if you gave like a kind of a big table, the scenario I talked before, it can be medical test mixed with democratic information, and such a big table, how can you get a causal relationship? So as I already hear from the previous panel discussion, there's a long history of causal discovery, like more just a given historical data that can be observational data only, or a mix of observational data and experiment data. We can use 3 types of methods to discover the causal relationship. So there is a recent review paper about it, and I think the work, for CMU, many different professors in CMU really did a lot of really early work about it. There's a book about the causal prediction and search, and that really explains all these different methods. Just briefly, there are these 3 types of methods are functional causal models. I think typical methods are like the Lingam, ICA, Lingam, etc. So I think one of the takeaway, like from Lingam, apart from ICA Lingam, apart from it's a really useful type of functional causal model, it also tells us in which case if you can assume any functional form or noise form, in which case the causal graph is identifiable. Another type of method is score-based method. And then this typical method is like a GES, like a greedy equivalent search, etc. And then there's also constraint-based methods, and these are commonly, you assume a graph is fully connected, you do independent tests as constraints, and you do orientation as the second step. So these are the method, I think they have achieved like a lot of great application success, for example, in natural science, and commonly work with domain expertise. And commonly, if you look at the literature, this method, classic method, there is a lot of limitation as well. For example, scalability, stability, etc. So let's just look at a score-based method a little bit more in depth. So what's the idea of score-based method? It is like as the left table shows you. So that's your historical data. So it's observational data. You have 4 variables. You just get these observations. And your target is your task. You want to find the causal graph, right? So remember, we need a causal graph to build a robust model. So we want to find the causal graph. So how it defines how can we find the causal graph is in general form a score, and tells you that the graph kind of gives the best score in some way will be the true causal graph. And the commonly used score, for example, BIC, this is one of the very commonly used score. And so there is also paper kind of really showing the score-based method and constraint-based method, they're all asymptotically correct, and they will lead to the same causal graph. And for some cases, it will lead to like a CP DAC instead of a DAC. But in general, it has a theoretical guarantee. But there is another question. So the number of graph increase super exponentially with respect to the number of variables. So even with 10 nodes, the number is already very, very big. And if you think about the previous education setting, we have all the questions that we can ask the students, and for an online education platform, the question can be millions level. So none of these methods can actually scale to this millions of variable level. Of course, with all this research, people don't just search the whole space no graph. There are a lot of new methods, like new relative, for example, greedy equivalent search, and there are many versions of improved greedy equivalent search as well. So in general, it kind of tells you some rule how to navigate through this big graph space so that you don't need to compute everything. So for example, greedy equivalent search tells you we do one pass just to add edge, then we do another pass that is just to reduce edge, so that it is more efficient to explore the space, but still scalability is still an issue. So the downsizing of the space is still limited. Okay, so then next question, what I have in mind is now I have been building deep generative models. It can be used in efficient interactive system. If I want to make it robust, I need a causal graph. Can we do it together and improve the kind of both application, the discovery itself and the interactive decisions system itself as well? So that is what we tried as one of the initial steps. So let's go back to the education example I showed. So what's the observation data look like? It will look like a table like this, but it will be much bigger. So there will be a lot of questions. I draw 5, but in reality, this will be in a million level questions. And there will be a lot of students as well, because commonly, just even in a school, there can be some of the students. And if it is in the national level or big education system, and there are also potentially millions of rows, these are students. Each student will potentially only answer very few questions. So the table is very, very sparse. So traditional missing value, so traditional causal discovery algorithm also don't deal with missing value. If there is missing value, people do a strict delete row. In this case, it's not possible, because if you delete every row with missing data, you have absolutely no data. So that's the first thing. You potentially want to find the causal graph that is can scale to really large number of variables at the question level based on this missing data. Secondly, so actually, if you want the causal graph to be useful, not only to be making your model robust, but actually make it useful for human expert. So they actually don't care about the question level causal graph. They care actually much more about topic level causal graph. So think about it. So most of these questions are grouped in topics. It can be the first two questions, their angles, the second two questions, their kind of divisions, let's say in this way. So these are grouped. I mean, in real life, under each topic, there can be tens or hundreds of questions, or even more, depending on the topic level. So what really helps the teacher to give insight is potentially on topic level. So if just in the desired word, what the causal discovery algorithm can do, should do in some way, is we want to discover causal relationship like with large data, partial observation, and have the choice to be either in variable level or in group level. And secondly, as we said, when we build this interactive system, we also want to predict the missing value if we want to build it together with uncertainty so that we can combine with this personalized decision making, etc. So I'll just give a solution overview. As I talked about the score-based method, you have different ways to construct your score. And
yeah, 5 minutes, Cheng.
Thank you. And so for the solution in general, we use similar deep generative model, but we also have learned the graph. So we construct the score so that the graph explains best observe the data. And because the graph, if you want to have a DAG constraint, so you want to search the graph through a DAG space, then you can also use a DAG constraint. There's a paper called No Tiers, so you can make this DAGness into kind of a regularization, kind of just tells you how many potential circles it is. So we can build a deep generative model to do that. And in this way, we wanted to respect to the graph, right? So instead of using everything, use standard deep learning, why not use a graph neural network? And for regular graph neural network, you also know the graph, but here we learn the graph at the same time. So the G variable here is just tells you the adjacency matrix, and based on the example of G, we use different graph neural network to update, to learn kind of the distribution. And this can still follow a variation of autoencoder and decoder structure. We can use similar tricks to handle missing data. We can predict the missing data, and then meanwhile learn the causal graph. And then think about it, when we predict the missing data, due to its respective causal structure, it also can generalize better because you only predict the missing data entry based on what's causally associated. So in this way, let's just see a very simple example. So there is a neuropathic pain data set. That's a simulator based on real world data set that have like more than 200 variables with around 800 edges. So with our model, this is variable level causal discovery task. So we significantly outperform our traditional method. And if we also make missing value manually to test it, we can also predict it better even than the partial Bayesian autoencoder I talked before. And so in this way, we can have one deep generative model that is robust for missing value prediction in a probabilistic manner that can be combined with different downstream tasks. And we have a scalable causal discovery algorithm that handles missing data in a data efficient way and also can predict this huge causal discovery tasks can be used in this situation. And with this type of model, it's actually really easy to handle in group level because if you know the group, for example, the task, we know questions are grouped in topics. So instead of single question to a single listener representation, we can group them. It can be different number of questions in different group. And then these different nodes will become in group level. Coming back to the education. So actually we have this real world data set, and that was one of the computation we run in NeurIPS. Last year, there is a hierarchical group relationship. So we just take the lowest one. So there is actually 57 groups. And we run this algorithm And so in this situation, we actually don't know the ground truth causal graph anymore. So first, because we have different hierarchy level node groups on the left upper corner of the table, we look at, even in the higher level groups, how many links are within higher level groups and how many are kind of between them. You can see more links happening between the topics within bigger, higher level topic, like all different small topics under number are connected more closely instead of number connected to geometry, for example. And secondly, we actually give our results to two education experts and evaluate whether the adjacency and orientation makes sense. And so the experts are giving the score of 1 to 5. 5 is like a totally makes sense. 4 is kind of makes sense. 3 is it can be true, but I'm not sure. Like 1 is like I'm sure it shouldn't be this way. So you can see that the score is actually like above 3. So actually, especially comparing to random, just as a reference, and another baseline that can handle this situation, we achieve much better score. So in some way, the discovery results in some way are agreeing with the expert opinion. And meanwhile, we can do imputation at the same time. In this situation, due to we're doing group levels, our latent space is a bit smaller. Still, we achieve similar performance as partial variation autoencoder I presented before. If in terms of accuracy, it is even slightly higher. If in terms of algometric, so in general, these two methods are at the similar level. So with this method, we can do all these things we want. We can plug back into the interactive system in the first place to do sequential decision making, but with the extra bonus that we have the causal graph now. We presented this causal graph to education expert who is actually in collaboration with Oxford University Press. They are actually reviewing their curriculum in teaching. And of course, we present the results, say, okay, this is the results, like this machine learning result, it can be mistakes. Just we hope this result, maybe there are something can be helpful. And they actually look at it, and this is original feedback. They get back to me. And they actually find this is very helpful just from the causal discovery results. There are a couple of really fun examples, for example, the line diagrams that was taught much later. And then they suddenly realized, because our graph somehow, there are many kind of edge connected to line diagram, and they realized line diagram is used to kind of form questions to students, used very, very often. So then they decide to move this earlier in the curriculum for real world teaching. So I just want to give you this example to show how this can be useful in real world scenario. And that concludes my talk. So hopefully I go through the journey of my research. I mean, there are still a lot of open questions, but I did focus on how can we make efficient decision just as human expert. We go through how to make decision under any data, and we could go through how to make this interactive system to be personalized and efficient, and we can combine with causality to make it robust and interpretable. So this concludes my talk. Thank you very much.
Thank you, Cheng. So are there any questions from the public? We have around 5 minutes for some discussion.